Okay, Yuchen, please start.
Okay, so today's presentation is going to be on debugging with intelligence via probabilistic inference. So these are the authors. The main author is Xu Zhaogui, a PhD graduate from Nanjing University. And he has a lot of research interests. Programming support, bug detection, testing, symbolic execution, probabilistic inference, and machine learning, and also recently reverse engineering and binary code analysis.
How about Zhao Gui these days? I just have a talk with him maybe several years ago. So have you checked his profile and where is he now?
I believe, oh yeah, he's working at the Ant research.
Oh, and
Ant Group
research back
Yeah.
in China. Okay. So I met him and discussed with his research idea when he was an exchange student in Purdue University. At that time, his supervisor is Prof. Xiangyu Zhang. Okay, keep going.
Okay, then the second author is Ma Shiqing, assistant professor at Rutgers University, and his research interests are system and software security, deep learning security, and program analysis and software engineering. Okay, so Prof. Zhang Xiangyu is the co-advisor for the first author. He's a professor at the Purdue University, and his research interests are in programming analysis and software engineering. Okay, so for this author, I couldn't really find much information on him. So yeah, PhD student at Penn State University. And then lastly is Prof. Xu Baowen. So he's a professor at Nanjing University, and he's the supervisor for the main author. Yeah.
Okay.
Okay, so let's go into the paper. So the paper essentially is an improvement on microbat. So the background is that, well, debugging is hard. And if we try to teach the program how to debug, we have certain limitations. And one of which being that the assumptions are too conservative. So for example, in dynamic slicing, all the variables that might affect the final outcome is considered into the dynamic slice. So that actually creates a lot of statement instances where the programmer would have to look through, or the programmer will have to look through. So on the other side, we have human debugging, and it can be fast because we have some intuition about the program.
Maybe have a comment here. Algorithmic debugging basically is somehow relevant to dynamic slicing, but it is actually an idea proposed to debug the prolog program. So the prolog program is kind of a declarative program like Haskell. So this algorithmic debugging is actually a way to, it also takes the feedback of the programmers, and I've asked a few programmers to say whether a certain variable is correct or not. But algorithmic debugging, since it is more towards the functional programming languages or declarative programming languages, so it does not take much about the control flow. And also, the idea is quite simple. But anyway, this algorithmic debugging actually proposed in 1980s. Actually, it's proposed in 1980s. That means it is 40 years ago. But the one who proposed it has won a very distinguished, I think, won a distinguished PhD thesis in MIT. The idea is still simple, very similar to our microbat idea. But anyway, just look into the data flows and still takes a very limited or conservative feedback from the programmers. Okay, please go on.
Okay, right. So we are saying about the humans. So the humans we have an intuition about the buggy program, and we have an idea of where to look, but we don't have the capacity and stamina to reason about the more low-level program semantics. Okay, so this is where microbat comes in. So we take human feedback into the debugging process. So the author's criticism to microbat is that the coupling is still very primitive, and we are basically doing like a more primitive, like a binary search throughout the slice. So the author is proposing that we use a probabilistic inference in order to model like all these hints from the program structure, from the variable names, in order to come up with the root cause. Yeah, so we can ignore the first wall of text. We can just look at the second and third points. So each executed statement is modeled as a probabilistic constraint. And then we feed this constraint into a inference engine. And then the inference engine will spit out the statement that is buggy. Okay. So this is the setup of the framework. So what we have here is that the my mouse disappeared. Okay, but we have the Python program. So it only works on Python for now. The Python program takes in is run. We generate a trace. So from the trace, we encode the variables into constraints. And then it will do some solving. And then after that, we pipe the outcome into a statement instance constraint encoder. So after we have solved the constraints on the variables, we create more constraints on statements itself. And then we solve the constraints on the statements to finally output a suspicious statement instance. And that will be given to the...
I think this is a very abstract workflow. And I suggest that it's better to prepare an example to see how the inference is going to make and how the constraints is constructed so that it can fit into the engine.
So I think there will be some examples later on.
Okay.
Okay, I think I'll just go like this so it's easier. Okay, so basically how the inference works, we have, there's two phases, right? Firstly, we create the constraints on the variable and then we decide whether each variable is correct or wrong. And then after we have the result from the variable, we infer on the statement. And then finally, we output the most suspicious statement. And then the user will, collects the same kind of feedback as microbat. It will ask for the correctness of the variables. So if the programmer believes that this variable at that instant is true, we supply a value of like 0.95 for true, and then 0.05 otherwise. So this will be feedback into the constraint encoders again, and then this cycle continues. Okay, so what are constraints? So let's consider the case where we have a simple assignment and addition statement over here. So x equals to a plus b. And from here, right, we can generate like 3 constraints. Firstly, if a is correct and b is correct, then it's also likely that x, the result, is going to be correct. And then similarly, if we know that x is correct and then a is correct, then b is probably correct also.
By the way, so here, you mean a is correct, b is correct. So we infer x is correct.
Yep.
And but what if, so here, where the feedback come from? So does the user specify both n and b are correct?
Okay, so at the start, it actually infers some of the things by itself.
Okay.
Yeah, so usually I believe that the line 1 is always going to be true. So they will feed it in for you, and then the last one is going to be false. Yeah, so and then these probabilities will propagate inside the system until.
So the probability is only assigned for variable. And how about the step? How about the step per se? So think about it. In our microbat, we have several assumptions, and we believe that the error could be everywhere. So So that means even we reach this step, it is also possible that maybe it should not be plus, or it should not be maybe it should be a minus operator used instead. So that means even A is correct, B is correct, X may not be correct.
Yep. Yep. That's
so
in phase 2.
Okay, so here the variable constraint is that so the user provide certain feedback on certain variable, saying that this variable is correct, right?
Mm.
Am I correct?
Yeah, yeah. So
okay.
some is also automatically discovered. So for example, like usually the first line of the whole trace, the first node of the whole trace is correct, and then at the end is wrong.
So the probability, the correctness probability is on variable or on step?
On variable for now.
Okay, so here it's on variable. Okay.
Yeah, later on there will be on step.
So here the PA means that the variable A is correct.
Yep. So this P, you read it as a predicate. So over here, PX is an assertion that this X or statement is correct. So in this case, it's just a variable. Yeah, but. Okay, so this takes a.
So will you please be more specific on the basic definition? I think maybe the definition is very important for us to understand the details. So what do these symbols means, right? So will you discuss these definitions later, or after these slides, those definitions were just gone? We will not use it anymore.
Yeah, we will go into exactly how the constraints are generated. So okay, we can spend a bit longer on this. Yeah, so basically, you just can just take it as like a true or false value. So this is we have a statement on A, right? So it just decides whether A is correct or wrong. And then given this kind of statements, we have each one here is a constraint. And then given this statement, we generate a few constraints. So this is one where if the A is correct and B is correct, and then X is probably correct as well. So this is a constraint. And then we have a few constraints. Okay, so now let's talk a little bit more about this thing. Okay, so basically, if we know that X is correct and then A is correct, in this case, it is likely for B to be correct also because this is a simple binary operation. But let's say that we are doing something like an access, for example, BI, okay? Let's say that we're taking BI. Then depending on what B is, it may or may not give us more idea about the correctness of B. So for example, if A is 5 and then BI is 6 and then X is 11, right? And then maybe we have we don't know whether I is correct or not. So if B is an array that is all 6s, then we cannot infer much from this statement. If A is correct and then X is correct, we don't know whether the I is going to be correct or not because B is all 6. So I can be anything, right? So in this case, right, this message that there's a propagation probability. So we determine a propagation probability based on the kind of statement it is. And that would help us decide what's the final probability for B. Okay, so in more formal details, it is like this. So we can look at it as it follows the notation of the paper. So this is one statement. In this statement, we have Z being assigned, V, the value being assigned to Z, or another variable being assigned to Z, or it's a binary operation between X and Y that's assigned to Z. And this binary operation
so here,
is
what's the difference between V and X?
V is
Constant.
literal value.
Or the constant, okay.
Yeah, it's a constant. So in this case, the propagation probability is going to be high. Yeah. I'm not sure if you're able to see the next one, but
yeah, so here, so this is just a condition, right? And so maybe just be more specific, this is a predicate, and or this is a precondition, and this is a postcondition, right? And what is this U about? And what does this U mean?
So you just reference to the output. So for example, you can see here, if you're trying to infer what is PB, then this P, the small p, is also B here. Does that make sense?
I think it's not very clear here. So we usually have the, I still cannot get a very clear clue here. So anyway, so we want to, the basic idea is that we want to infer the probabilistic whether a certain variable is correct or not, right? And
yep.
So what we have is about the observation. So the observation include, so first includes the user feedback. Sometimes user infer, or user will told us whether a certain variable is correct or not. And also based on the program structure, or this structure basically can form the constraints. So when user gives a variable saying that this variable is correct, and we're giving such a variable a probabilistic of 0.95 to be correct, right? And based on the program structure, such a probability of being correct is propagated through all the variables around the program structure. So that's a basic idea. And can you be more specific? Is that so? The PU and what is U means, and this is a statement here, right? And it can be more specific or raise an example. And when we need to apply this predicate or this basically this is a rule, right? So when we meet such a preconditions and we have such a post conditions for the inference, can be more specific and raise an example when such a statement happens and why we will infer PU to be high.
Yeah, so let's go back to the previous example of just x equals to a plus b, right? So in this case, we have x being the z here, and then we have a plus b, and then this binary operation is plus, so we fulfill this these two preconditions, right? So when we generate the constraints, it will look like PA, PX, and then PB. So this is just saying that regardless of what the what's the target, right? The probability is high. Okay, so perhaps this, yeah.
And I still maybe that. So what does U means?
PU. U is just a reference to the variable. So in this case, it's you can look at it as X or Y.
Okay.
They both apply. Yeah. So maybe this one will be more clear. So let's say that we have X equals to Z equals to X mod Y. Right. So we can generate, we want the reason about PX, for example. So there is PZ and then PY. Right. So this is just saying that, okay, so this is the statement, but if we are trying to infer what's the outcome on X, we are uncertain because there can be a large number of values of X that satisfy X mod Y equals to Z. So the probability here is uncertain. And uncertain takes on the value of 0.5. So we just don't know.
How can they assign the uncertainty as the probability of 0.5?
Yeah, so basically 1 means that it's true.
I
and
got
then
it. I got it.
0 is false.
I got it. So
Yeah, so if the value is very low, then we are more sure that
from a
not.
philosophical point of view, the probability is the uncertainty among those. The probability, the information probability is the certainty for the uncertainty, right? So since since the value is uncertain, I think it's not that convincing for me, not convincing to me, saying that we assign just a probability of 0.5. Maybe it should be uncertain. Just like a variable, the variable is more, basically it's just a random variable, right? And how can we just assign the probability or distribution of the random variable into 0.5? But anyways, that is just my comments for me. Let's keep going on. I think it's better for us to go through these rules one by one. It was better for us to grasp the general idea.
Okay, then we shall. So just keep in mind that the general idea is as long as it's possible to map your values of x and your x and y to z, as long as it's a one-to-one relationship, then the propagation probability is a lot higher. Whereas if there's many to one, then it's unclear, but it's not necessarily false, right? So in this case for AR, this is looking at object attributes relation. So let's say that we have y equals to x dot f, then the value probability for x is going to be whether there is a lot of different objects with the same attribute f that can be accessed, and then that gives y, that gives v. Okay, so in this case, we also run it through this function in order to.
So let me recap here. So the idea is that assuming the user have been saying that y is supposed to be correct, right? And when we dereference f, it depends on how many f in the program with the same value of such y, right? And x supposed to be O. And how do we read these rules? So this is the phi is actually a condition, right?
The phi is just a function to return it returns a probability.
Okay, and how
yeah,
and
so
in this case, how could this O dot F to be high? The high means higher to be correct, right?
Yep. Yeah, because we know that we already say that y is correct, and yeah, so definitely O dot F is also going to be correct. But the issue is whether the variable x is pointing to the correct object. Yeah, does that answer your question? So this is.
Yeah, I think there's a guess here, right? There's supposed to be a guess here. Okay, keep going on. But anyway, I think those rules at least provide us some guidance. But I think their rules may not be 100% correct.
Yeah, it's like very heuristical.
Yeah, and I think so they just, you can think about this, they write a lot of heuristics into formalize their heuristics, but even the formalized heuristics is still heuristics. And there's many possibilities, supposed to be, and maybe, and how about the O here? So suppose Y is supposed to be correct, and maybe they are not using the correct X. Right? Suppose I'm using another x prime dot f, and the real stuff supposed to be x prime dot f, right? Then then still, and what is correctness of x prime or the O, right? O is actually a memory address, right? Maybe they reference the wrong memory address, so that is also possible. Okay, keep going on.
Okay, so this one is memory access. So yeah, so actually if we just slowly read, and then it's the same concept as back here. So if we have y and then we are accessing the ith element of x, then the probability that x is correct or wrong is determined by the number of collections having value v at index I. So index I is this one, and then basically how many arrays with at index I where this is the same value, right? So if this is A, then how many arrays there are that also have A in their ith index? And then you count that number.
I think Xiangyu's paper, maybe it's not a problem with Xiangyu. So I think their paper have a lot of the, of course, it can be correct under certain scenario, but it is not a generally correct idea. I get the point, but I think I still have some concern for these rules. It is also possible that maybe it is not. It is also possible that if the array X has the correct X hasn't been created, right? It also possible. And why we just go through all the array, and then maybe some correct array has not been constructed, so that the error happens. Have I get myself clear? So what I mean is that the idea is that it is going to search all the array in the program, right? And to see how many arrays with the index I with the same value, right? So that is basically his probability. But I'm talking about is that it is also possible that this array, the really, and this array is incorrect, but the correct array has not been created. It's also quite possible, right?
Yeah.
So that is problem debugging. So basically, their approach is targeting for some general bug. Usually, the debugging research works in two aspects. The first is for general bug. That means give me a program without a bug, and whatever bug it is, we're trying to debug it. And the second aspect is that we focus on some specific kind of bug, for example, concurrent bug. We know that there are some data race problems. Now there's a deadlock problem there. And how do we fix that? So there's two aspects. But for this general bug, the challenge lies in that the bug can happen for any reasons. And now they have narrowed down the possible reasons. I'm not sure whether they're discussing the threat to validity. Okay, keep going on.
Okay, so do I still?
Yeah. We go through the rules here.
Okay, sure. So let's look at in this case of a conditional statement. So we're looking at the x and y predicates. Okay, so we are comparing equality, right? If we know that x is, if we know that the value of x is actually the same as the value in y, in other words, this is the
true, right?
predicate, evaluates the true, and then we can conclude that both are highly probable to be correct.
Why?
Yeah, because this is the one-to-one mapping. So if one is true, then and x and y are equal, then y is probably true also, and vice versa.
It is also necessarily true. Maybe I think that paper kind of the okay, but anyway, we can but anyway, is Xianghui there? Hello, Xianghui.
Hello, yes.
Yeah, I think we may need to, since for our debugging work, Yuchen is focused on the fundamental infrastructure, and your work is more focused on the intelligent reference. I suggest that you pay attention to this presentation, at least if it is actually a baseline. So you can see there are so many problems there, but this problem is not a, it's not a formal problem of formalization. It is a problem of manually defined heuristics. There are so many heuristics there, and it's very easy to find a lot of contact examples. And we're supposed to propose a more general and a more intelligent inference, of course, based on their idea. And I think I do have some idea in mind, but I suggest you pay attention. I think maybe this is also a part you can, I think you can implement their approach. But anyway, that is the baseline. I suggest you pay some attention.
Yes.
Okay. And as for now, do you understand the majority of the discussion?
Roughly, yes.
Okay, so maybe you can just raise the questions if you're not grasp the most idea, and we can recap it because Yuchen is very good and he goes through all the details. You can have more discussion with Yuchen on offline. Okay, Yuchen, please go on.
Yeah, so if anyone else also feel free to ask questions. Okay, and so the opposite is when x is not equals to y. So if they are not equals, and then we know, for example, if we know that x is correct, we cannot make any deductions about whether y is correct or not, because like for any, let's say like a value 1, right, then y can take anything that is not 1, right? So anything in the real number space that's not 1 will make this predicate evaluate to true. And so we just cannot say anything about the correctness of x and y, and therefore they assign the probabilities to 0.5, which is uncertain. Yeah.
So basically, we can just rewrite the operation here. So suppose whatever x equals to y or x not equal to y, we can have a Boolean variable writing x equals to y, or Boolean variable like x not equal to y, right? So based on idea, we know that x is correct, and after x is correct, we're saying that x equals to y, and both the probability of x being correct and the probability of y being to be correct will be high. Otherwise, we're saying that they are uncertain. And I think that is not in that world. So suppose the b equals to true, right? And x and y, suppose there's an infinite number of combination of x, y to satisfy that constraint. But of course, the number of combination of x, y, suppose b is equals to f, the number of combination of x and y to satisfy the constraint is much larger. Have I made my point? So suppose here, basically there's constraints. The constraint is that x equals y is true, right? So this is just a constraint. Assuming that we have already known, so here the problem is that we have assignment. Suppose x equals to 1 and y equals to 1, okay? And assuming, so here the problem comes to that given this constraint, we know x equals to y is true, and also we now given assignment x equals to 1 and y equals to 1, and what is the probability of both x and y to be true is correct, right? And given their rules, they're saying that they are very, very likely to be correct. But the problem is that if x and y are real number, they are in maybe 2 to the power of 32 combination of x and y, right? And x could be 2 and y could be both x and y can be 2, and both x and y can be 100. There are so many possibilities, and why we infer the probability of the event x equals to y equals to 1 is very high to be correct.
I think that we don't necessarily know if x is equal y. So in other words, we don't know if this conditional is supposed to be true or not.
No. I'm talking about this rule. I'm talking about this rule.
Yeah.
So here, if I'm reading correctly, so giving the condition x equals to y is true, right? And definitely, and we want, and then it became, and this rule tell us that the probability of x being correct and y being correct is very high.
I think it's at this part where x equals y is true. I feel that at this stage, right, we are still not making any assumptions about whether the result of this is true or false. We are only saying that we got high confidence in the value of x. And
but
then
if we do not have the assumption of x equals to y to be true, and how do we infer the value of x being correct is have very high probability?
this is the dynamic slice, the result of the dynamic slice. So during the execution, this happened, right? So we evaluated this. So we don't know whether we should be evaluating this or not. But we only consider the values in x and y first. Since this has executed and then we got high confidence on x,
then
this means
it becomes even more problem. So if we just have a dynamic slicing and reach this slice x equals to y, right? And now we even do not know whether this value is supposed to be correct or not. If we do not have this information, how can we further infer px is high and py is high? It becomes even harder for us to make such a judgment. You can think about it. So if we do not know whether x should be equal to y, right? So this event, whether this condition to be true is unknown. And how do we know x equals to 1 and y to 1 should have a very high probability?
I think this is just the confidence that the no. When px equals to high, right, this just means that the predicate that we are evaluating has a high effect on whether predicate x is true, is high. Let me try to.
Okay, so you can try it again. So high equals to 1, right? Low equals to 0, and uncertain equals to 0.5, or something like this.
Yeah.
Okay, so maybe you can interpret it. So the px. So you can see the px assert a variable statement instance is correct, right? So the high means correct, if I understand it correctly.
Yes, but this small px, this one is the propagation probability. So we have another predicate over here, right? And then if this is true, then it has a lot more effect on whether px is true. That's the value. That's the value that we are talking about here.
Okay, so it's about the inference probability.
Yeah.
So the high and the low means or strength, the inference strength here.
Yeah. Yeah, for all this small piece. So
and here. Okay. Let me think about it. So if x equal to y, if we know this happens, then x, y, and both x, y have a high impact on the event it happens. And otherwise, the value of x and y have a low inference, or have a lower inference for this to be happen. And let me think about it. So can you further interpret it? Maybe can you further interpret it than this statement or this rule here?
so for this statement, x is not equals to y, and then so when we have a predicate that is constrained onto x, right? Big P here, then the effect that they have on px is lesser, 0.5.
So basically, if x not equal to be y, the predicate, but we have to know whether, but I still have, maybe I'm a little bit confusion here. So, but we still have to know whether this statement or x should be not equal to y. We have now this issue, right? Have now this effect.
Yeah, we haven't gone through that yet. Yeah, so yeah, this paper is quite hard to understand for me also, but okay, so hopefully it's a bit clearer now. Okay, so we have a question: what are the bounds for psi? So what's the upper and lower bound for this function?
So mean the bounds of probability.
Yeah.
So it depends on the range of being high, right?
Yeah, so let's just set it as 0.95.
And it also depends on the range of n. Right. So maybe you can ask some way to make a guess.
Give me a moment. Wait, so high is 0.95. Or is a range? Okay.
No, high is a constant.
High is a constant. I'm not too sure.
Maybe for easier calculation, you can just let high to be 1, right? So let me try to remove 0.5. Let high to be 1. It could be easier, right? Easier to be calculated. Otherwise, you still need to do some arithmetic calculation.
Okay. The range, right? It's definitely more than 0.5, but less than. Then the other bound is, yeah, okay, so it's open at 0.5 and close at 1. Is it?
Yep, correct. Close.
Because high now,
right?
the high now is equal to 1.
Yeah.
So I think it might be correct.
0.5.
And also it depends on Yuchen. So what is the range of n? Whether n start with 1. So that is my question.
Yeah, so whether it ever is 0, right? No lah. So if you look at the way that it's used, it's always going to be 1 or more, because if such a statement can exist, then
at least
itself,
one.
yeah,
it appears at least once.
Yeah. Yeah, correct. So essentially, this just means that the more occurrences that the more repeated possibilities there are, then the lower the certainty. Yeah. So it just goes back to this two. So okay. Okay, so any more questions so far?
And also, let me think some inference details. I'm still thinking about these, whether this makes sense. The number of array list, the number of inference. Okay, let it be, let it be. So, Xianghui, I hope that you understand the details, because I hope that you are supposed to be the one who implements this baseline. And I have my final question for these slides. Have the author mentioned about the method invocation? Because these are all the basic program primitive, like the array access or object access, right? So object access, array access, and the binary operation, etc. So what if it is method call mxy, and how do they inference such a case?
I do not recall seeing the author talk about it. I think they mentioned that they translate all the statements into the static single assignment. I'm not sure if that helps.
I understand. So think about it. They do. So maybe you can be introduction a little bit, at least to Xianghui, what is SSA means.
Okay, so static single assignment just means that you can basically look at it as like the CPU instructions. So there's always some value, some operation, and then another value, and then it's assigned to a third variable, sorry. So all the program takes is basically expressed in this form only. X equals
maybe
y,
I try to
example.
explain a little bit. So here, so in the program structures, we probably will have a equals x plus y and a plus plus. Okay, right? So in this case, despite we use the same symbol of a, but this a has been redefined in the second line, right? So when we do the program analysis, usually we need a way to distinguish the first a and the second a. So here we will assign the first a as a0, and for the second a, we means a1. A1 means a0 plus 1. So that means each variable in the program will be assigned only once. So that is called SSA form. And this technique will be heavily used in symbolic execution, because when we are executing the program in a symbolic way, we need to be very specific which variable it is during the execution. Have I made myself clear?
Yeah.
Okay. Yeah. So let me come back here. So my follow-up question is here. So suppose let's be S equal to BZ equals MXY. Okay. So suppose we have such a form, and what is so now we try to infer what is PX and PY. What is its inference to Z? And this is supposed to be a challenging question, right? And inside M is supposed to be a loop. Suppose I write M into a very complex form. While X equals Y, and then X plus and Y maybe times Y whatever times 2, whatever it is. And then we can do some more complex calculations and then return it back to Z. Right, it's all possible. And what's their inference? Supposed to be unknown, or there's an analysis for this. I think this is a challenging but very realistic problem here.
I'm afraid that the author has glossed over it. My guess is that he just unrolls the method, so all of this is part of the It's just one whole list, like one whole very long SSA. Yeah.
I think
And
it is
then-
not a heuristic. And also, what if the socket, if there A comes from a socket communication, right? So we do not know what X is. And also Y comes from the native library call. And what if that happens? There's always a way that we miss the data control causality here. So if based on their solution, because the mode can be looked into, can be considered a special form of function. But I don't know why they only look into mode, and basically they have a lot of the other operations like shift, etc. Right? And they will have uncertain. So in this case, I think the relation of px or the variation of px is supposed to be uncertain. That is based on their logic. And Xianghui, I'm actually talking about if we want to implement their methodologies, and how do we handle a lot of corner case here?
Okay.
Okay, Yuchen, please go on.
Okay, so now we go into the part about inference. So as we say, each constraint becomes, so we generated a lot of constraints from here. And then actually these are the constraints. So we have a lot of constraints, and then each constraint we have some probability, propagation probability, which we calculated with this. And then afterwards, we need to try to solve the
I do think their rules is not enough. At least the rules defining their paper is not enough. Have they open sourced their project?
No, I tried looking for it, but I couldn't find any.
Okay, so because the first author is my friend, so if necessary, we can add him in our group and have discussion with him. Okay, please go on.
Okay. All right, so basically now we express the constraint as a function. So this function fi corresponds to ci, where c is the constraint. And then this is just p if the constraint is true, and then 1 minus p otherwise. And p in this case...
Sorry, so how did this ci come from? Where does this ci come from?
C is just the constraints. So you just pretend that there's a label. So let's say that, let's say that this one is 1, and then the constraint, it will be C1. It will correspond to this line. Yep.
Okay. And basically they are inferencing that the user have a probability of 5% to be wrong, right?
Actually, no. So this is 0.9, right? Is just because that you should never use a full 1 or 0 in the probabilistic inference engine.
Oh, really?
So you want to represent true, but you cannot use 1. If not, I think it messes with the accuracy.
Okay, so in that case, suppose the probability is 1. If we want to propagate the probability back, and it will always decay, right? The probability will always have a decay there.
Yeah, but if you set it to 1, then there's no more decay, isn't it?
Let me see what. Suppose here x equals to a plus b, right? Suppose we have already now x supposed to be correct, and how do we infer the probability of a and b to be correct? And we know that, and you get my question? So we know that the propagation probability is 0.5. And here we just know that the inference of A and B, both the inference of A and B to X is 0.95, right?
Yeah.
And when we try to propagate the probability back, and how can we do this? Assuming that we know X is correct already.
Yeah, so it generates multiple constraints. Actually, yeah, so this is one of them. So let's say that we have 3 variables, right? Actually, there are 3 constraints. One with A and B, one with X and A, and another one with B and X. Yeah. Yeah, so that it generates a lot of constraints.
In a conjunction or disjunction manner.
Conjunction.
Conjunction, it means that
there are some cases where it's a negation of that also.
so all the relation are conjunction.
Mostly, yeah.
And can you write the conjunction down? So it means that suppose we know the Px is true, right? And then how do we write down the formula of PA and PB? Oh, here we should use this one, right? And also how do we know the value of PB? Because we have not decided the predicate of PA, right? Suppose we only have feedback on X, and how do we know the predicate of A or B? And then how do we infer B, the probability of B? So this formula only tells us that we know X is correct and A is correct. And then the probability of B to be correct is 0.95, right?
I am not sure about this actually, the final value.
But anyway, so there's always a way. So you can consider the probabilities just like a water reservation. So the whole graph or the whole trace graph is just like a lot of river. Maybe it's much richer reservoir, and there's many reservoirs in the. So in my imagination, if we consider using a metaphor, and each variable supposed to be a reservoir, and the water are flow across those reservoirs, right? And we now, when we have a feedback, basically we are inject a lot of water into one reservoir, and the water will flow across those reservoirs, and based on their predefined propagation probability. Right?
Okay, if you are saying like where can we find the first instantiation of the variables, right? So they start from the end and the top. Yeah, so for example, if B is initialized first, and then at the end of the program we print X, and then we say that this one is wrong, right? So usually we have this one to be true first, so we set it as high, and then we set X to be low or wrong, and then yeah, so we solve the constraints, and then it will figure out.
Maybe we can show more example here, but I do have a lot of questions about their inference, and also my concern is about the omission bug. So omission bug is that just you mentioned, suppose X is equal to B, and of course because this is one-to-one mapping, if we go to B equal to 0, and we believe B is correct. In this case, the bug must lie in that the X should be assigned, or B should be assigned somewhere else, right? But it hasn't been assigned. In this case, how do they estimate such a probabilistic?
Sorry, can you repeat that again?
The problem. So let me be more specific. So X equals to B, right? And B is equal to 0, right? So there's supposed to be a causality relation here, right?
Yes.
And here, so as you mentioned that the propagation probability is 0.95. Okay. Anyway, it's supposed to be high, right? And suppose the user provides that this X is wrong, is incorrect, and here it's supposed to correct, right? And then the only reason is that either X or B should be assigned somewhere in between, right? But it doesn't happen. In this case, we call this bug as omission bug. So when the bug happens, it usually consists of two reasons. The first is that we do something wrong, and or we didn't do something correct, right? So anyway, there's two reasons to be blamed or be responsible for the final fault. And in this case, and the omission bug is actually talking about we didn't do something correct. In this case, how do we estimate the probability?
That's a good question. I am not very sure actually.
Yeah, but anyway, so let's stop being expanded the topic, the discussion topic. Let's count it back, and I suggest that you can show some examples there for us to better understand such an inference.
Yeah, I have one long calculation example coming up. Okay.
Okay.
So, okay, let's I copied the actual formula so we can look at this instead. So we have F to represent the constraint, and then we have a lot of constraints, right? So we model all the constraints in conjunction, and in this case, it's just a product of all across I, of F across I. So yeah, so we have a lot of constraints, and all of them must be true, right? So we just like conjugate all the constraints together. Okay, and then we define the joint probability of joint marginal probability of all the random variables here as basically like this. I think this one is okay. It's just function definition, and then so this is apparently what we are trying to find out. This is the posterior probability of xi. So for example, we take this, we follow the same x equals to a plus b example. Okay, so in this case, x equals to a plus b. We have two constraints, right? One is that the variable xi is, sorry, this is a predicate. So x1 is basically like this. And then we are saying that a and b corresponds to 3, and then these two. Okay, so we have these two constraints. Now,
so here, let me confirm. X is a predicate. Xi is the predicate, right?
Yes, yes.
The predicate means that the variable x is to be correct, or how do we read it?
Yeah, correct.
So that means the value of x to be correct and the value of the x2 to be correct will have 0.5% of the inference to say that the variable x3 is to be correct.
Yeah.
Okay. Okay, keep going on.
Okay, then we have a probability function. So this one corresponds to the f that we just talked about. So it is 0.95 if the whole constraint is satisfied. Okay, so there are some caveats to this, right? So let's say that x1 is false, and then x2 is true. And then in this case, what happens is that the constraint is still satisfied because this is vacuously true, right?
What?
So
suppose it's supposed to be false, right? x1 is 0, x1 is 1, and x conjuncted with x2 is 0, right?
Yeah. So this is false.
Yes, false implies true, but also it means that x3 is supposed to be true, right?
x3
is true. Then this function or this equation is supposed to be satisfied.
Yeah. Actually, it can be false also. Yeah.
Oh yeah. So whatever x3 will be, is chosen, this four expression will always be evaluated to be true.
Yeah. Okay, then what happens now is that we basically.
Oh, by the way, how do we read f1 x2 x1 2 3? How do we read this probability function?
So recall that it's just a constraint, right? So let's say that we have some x1 and x2 is
and
x3.
this p is a predicate. Okay.
Yep. So notation is a bit quite convoluted here. So yeah, then the final result that we're trying to calculate is something like this, where what's the probability that x1 is correct, and then this probability is calculated like this, right? So that's the
okay. So
that's the sum of the.
Let me read it a little bit. So can you interpret this formula a little bit?
So.
And what is F2, F3, F4 means?
Right. So this one corresponds to here and here.
Okay, let me see. Constraint.
Yeah, so remember that there's like a whole list of the joint, I think it's joint marginal distribution, the probability function, right? So when we want x equals to 1, we're basically summing up all the other possible values of x2 and 3. So this is why we have this.
Okay.
Yep. And then yep. So what's the value of f1 if we insert values 1, 0, 0?
Okay. So I suggest Xianghui, or maybe you can try ask someone. But I think the other students or the other audience may not that follow into these slides. Maybe Xianghui is the only possible candidate can address this question.
Yeah, it's quite a hard paper. So Xianghui, would you like to try, or maybe I can ask somebody else?
Hello, Xianghui. Hello, Xianghui.
Yeah, hold on. Sorry, I'm looking through. Yeah, I just came back from the toilet. I think you have to ask someone else. Yeah, I just came back.
Yeah. we give Xianghui a break. I don't know. Ruofan, maybe. So actually, you can try to just read off this table. And try to guess the.
You can maybe just write it down, write the formula down. No need to be the direct, because the calculation kind of be complicated. You can just write the formula down. Because the formula is just there, the value will be there.
And actually, there's no calculation. So. So this is the constraint that we are trying to find out, and then here is 1, 0, and then this is 0.
Does this row has some relationship with the other rows?
The value here is the answer, so I blanked it out.
Okay.
Actually, I give it a try.
Yeah.
Okay. Is it 0.95? Then 0.95.
Yeah.
Then 0.05, and then 0. Yeah, and then I think 0.05, 0.95, if I'm not.
I think you're correct.
Yeah.
Yeah. Yeah, so that's it. Okay. So basically the framework that the author proposed, right, finds the posterior probabilities of the whole system using an inference, like an open source inference engine. And then the implementation is something called the belief propagation. So I'm not exactly sure like how it is, like the details of the implementation, but apparently it's like it's a machine learning technique. Yeah, and then the algorithm is called the sum product algorithm. Okay. So after we are done with the variable constraints, now the posterior probabilities are used as the prior probability, like so it's used as the input to determine statement probabilities and to generate the statement constraints. And the statement constraints are listed like so. Okay, so we slowly go through. So P predicate here refers to the control dependency. Yeah. And then actually def refers to the definition. So for example, x equals to a plus b. Then the def here refers to the x. And then for every u in the user, so each u is a and b. And then, yeah, so this statement has a control dependence on maybe another statement. So then the predicate of that statement is p pred. And then finally, this gives us the propagation probability, or the target of the whole probability of the statement. Okay.
Okay, keep going on. And by the way, so here that means if I think, but I don't know how to interpret this, but I find the requirement so strong, right? So we need to know that the control statement to be true, and the definition to be true, and all the rest of the variable to be true. Then we will say that this instance, or this instance means this statement, right? This statement to be true. Okay, so that means everything is true, and then we know that this statement is highly likely to be true.
Yep. So then the other cases are, let's say that if in this case, so if the result here is wrong and all the users are correct, then the statement is not true. Yeah. So if all the operands are we have a high confidence, but then the result we say is not correct, then this the error is here.
But what if there does not exist such a predicate? The control statement does not exist.
Then I believe they just ignore it.
Okay.
Okay, so this is variable to statement constraints, and then another class of constraints we have is the program structure. So this is very heuristical also. So how this is calculated is just whether there is like a lot of statements in the very hard to articulate. Okay, so let's say that there's a function, right? And then we do a dynamic slice, and then we realize that this function has a lot of lines that is included in the slice. So if this is the case, then perhaps this function, the error is from this function. So we set this to be very high. And on the other side,
is that correct? Is that correct? Maybe the error is propagated from the input or the function parameters.
from the
Right.
function.
So consider
Yeah.
consider the return value is incorrect, and the reason might be the input of the function is incorrect, right? So every statement in the function will be sliced in the data control slicing, and then you say this function is supposed to be highly incorrect.
Yeah. So I feel that it doesn't really cover all the cases. The reasoning that the author said was that it probably falls into this case where the number of statements in this function is a small proportion of all the statements in the function. So that helps to offset this case a bit. But it's
no wonder
it's all
no wonder
very
this paper until now have only less than 10 citations, because the first is that I don't know whether it is a problem of writing. I think it make a very interesting and intriguing point is that they use some very advanced technique like a probabilistic inference engine, and they were actually basically they're just turn the program into a set of the events or the first logic proposition, right? So there are so many inference here, but I just wonder how likely it is, how practical it is. Maybe you can keep going on.
Yeah. Okay. So that's this constraint, and then lastly, it's a naming constraint. So this basically measures the similarity between the variables used in the line and the name of the function, and the variables used in the statements. So is a NLP kind of approach, and the details are actually
maybe the NLP approach is most useful. That is a more heuristic. That is a heuristic inside the heuristic.
yeah, and the details are not explained in the paper, but I went to look at the paper that it was referencing. They mentioned something about k-means and super vector machines, but I don't really know how SVM works actually. So I'm
SVM is basically a classification model. You're just doing classify. Maybe you can classify whether it's similar or not. I don't know how to judge this paper, but anyway, it is accepted, and also there's a lot of interesting. I think the idea is correct. The idea is correct, but anyway, let's keep going on. So I think that we'll almost reach the end of the methodology introduction, right?
Yeah, that's all actually. So basically, after we have listed all the constraints, right, then it goes through the inference engine one more time, and then we basically have yeah, so it just returns the lowest p, the statement with the lowest p value.
Lowest p value. What do you mean by that?
So remember that we have the
and also I have
something like this.
And also I have a question. So this is also somehow like a model counting problem. I'm not sure whether you know about the model counting. So it's trying to enumerate all the possible cases of a certain condition and calculate the probability. Here I'm think about so here are the questions. So giving so many constraints here, right? So it means that each time the user will provide a feedback on certain variables or on certain statement, which is saying whether it's true or not. It will recalculate the probabilities or recalculate the probability, right? Or again.
Yeah. It will just redo everything.
So what is their runtime overhead there?
It's surprisingly low. Let me. Yeah, okay. So this is the time taken to do tracing, and it's in seconds. So this is all like quite low numbers, and then the solving the constraints take yeah, like sub-seconds, sub 1 second timings.
Okay. Okay, let's keep going on. Okay.
Yeah, so okay, so since we're already here, the author benchmarked the program against two different classes of inputs. So we have like real world programs. These are the kind of open source library that is in Python, and then like those large open source projects. Yeah. Okay, so basically they found out that it requires a lot less interaction as compared to microbit.
They don't implement microbit correctly. But anyway, I don't give comments on this part. So I have another question. Is that so in this case, so what kind of feedback do they have?
They take the same feedback as microbit. So like we give the user one statement, and then the user decides if the values in the variables are correct.
And also, how about control flow?
They did not.
So we have a wrong bar feedback, right? We have a wrong flow feedback saying that this statement should not happen here. So this step should not happen at all. So we go to the control dominance, or to go to their control dependent step. Do they have such a feedback? Because it seems to me that all their their constraints is more on the data flow there.
Yeah. I think that they rely on the data flow to slowly bring the user to the control flow statement.
Maybe I need to go through the detail of the paper myself. And I think the probabilistic inference is really an important topic and it'll be useful. And also, I think that's a way we need to consider. And also, we may use some AI technique, just like Xianghui we went discussed. We're using the AI model to make a prediction. Use AI model to make a prediction. In this case, we are combining more general project knowledges, not just the probabilistic inference per se. But anyway, I think their approach, at least we need to briefly implement their idea. For example, we implement their inference engines or their probabilistic inference technologies. In this case, we can make a comparison there. Okay, so yeah, so maybe I need to go through the details, or somewhere I need to have a comments, and you need to pay attention here. So I think all over, when we go through the debugging process, based on our infrastructure, the problem of debugging will be transformed into a problem of finding the first 40 step on the trace, right? So our ultimate goal is that we will speed up such a trace traveling process towards the root cause. And here, this probabilistic inference, and Yuchen, maybe you can correct me if I'm not correct. So here, each time we're going to choose a variable with the largest or with the least probability to be correct, right? Each time they were just giving such a feedback and go through the trace, right?
Yep.
Okay, so in this case, we need to propose some more novel technique to address this issue. Maybe we can discuss later, and I myself maybe check this paper. I think this paper write in a very user unfriendly way. Maybe I can have a discuss with the first author to clarify their details so that we want to re-implement their approach. And when I get the details, I will organize the meetings and to be more specific. But anyway, the topic, the idea is correct, but in terms of their heuristics and I still have some concern. Okay, Yuchen, please go on.
Okay, so other than that, other than that, he goes through the effect of setting the values of high. So high is their only tunable like hyperparameter, and as you can see from here, actually there's not much difference between different values of high. And finally, we look at what's the effect of all the statement constraints. So there's variable to statement, and then variable to statement and structure, and then the one with the naming and everything. And in general, it seems that each constraint does contribute a bit to the final result. Yeah, so this one is the number of interactions, and lower is better.
Okay. Okay, maybe we do not spend too much time here now. We need to proceed to our next talk. My comment is that this paper basically is a baseline, and Xianghui was supposed to be implement this technique later, and that is quite relevant to the FYP research project. And we're supposed to propose a new technique to better to overcome and beat their approach. And I think there's a very promising area in this range, and in this duration to overcome or to beat their approach. I think the AI model is a very interesting topic for us to explore. And I think their NLP technique might be useful, or might be the most useful component. But here it seems that the naming. So is there a comparison between the yellow and the blue part?
It seems like there are some cases where it increases and some cases where it decreases. So
okay.
It seems like quite even.
Okay, but whatever it is, I will organize a meetings with the first author after I read the paper myself, and especially for some details. Okay, thanks, Yuchen. Let's call in for the presentation. Thanks for your preparation. It seems that I can see you all spend some work to understand the details, and I will discuss with you later if I have any confusion when reading the paper.
Okay, thank you.
And thanks, Yuchen. So next one is supposed to be Ruofan. So, and the previous talk seems to be a little bit narrow in a narrowed area, because it is more towards probabilistic, constraint extractions, and engine inference, and the topic is about debugging. But I think everyone has the experience of debugging. So here, Ruofan is looking to targeting for a more general area about AI topic, and that is part of the science model learning or the metric learning. So Ruofan, now please go on.
Okay, hello. Today I will present the paper called Uniforming Mutual Information View of Metric Learning, Cross Entropy versus Pairwise Losses. It's published in ICSE 2020. The first three authors are PhD from ETS Montreal. Last three authors are professors from ETS Montreal and this French university. Their overlapping research interests are computer vision and information theory.
Okay.
So this paper is talking about metric learning. I will first briefly introduce what is metric learning task. In metric learning, you want to learn an embedding scheme such that objects from the same class are mapped to neighboring embeddings, and objects from different classes are mapped to far apart embeddings. For example, I have a picture of baby who is wearing pink clothes, but I have another picture of the same baby, but he is wearing blue clothes. So if I call the first picture anchor image, second picture is a positive image to the anchor, then I will expect my model to have close embedding for these two pictures. However, here comes another picture of another baby. Since the identity has changed, so I will expect the embedding of my negative image to be far from my anchor image.
Okay, so that is very straightforward, and I think, yeah. So I encourage every audience here to raise questions, so we can have a more detailed discussions. Maybe we can have more insights during the discussion. Okay, Ruofan, keep going on.
So if we consider how the metric learning task is trained, this is the common loss called contrastive loss in metric learning. So given a triplet means, like in previous example, we have an anchor image, a positive image to the anchor and a negative image to the anchor. The loss has two parts. The first part is the distance between anchor and positive sample. Second thing is the distance between anchor and negative sample. So this distance is in the embedding space, not in the input space. And if we want to minimize the contrastive loss, then we are pulling the D positive to be small and pushing D negative to be as large as possible. And we have a third term here. This is a hyperparameter margin. That means once the discrepancy between D negative and D positive is sufficiently large, then this loss will become 0. We no longer put penalty on this triplet. So an graphical illustration is like this. So initially, my D positive and D negative are close. After some rounds of optimization, the discrepancy between D positive and D negative is widened. After this gap is larger than or equal to M, then the loss will become 0. So this triplet has reached the optimal. We do not need to further optimize because we think M is large enough.
Okay, so maybe I raise a question here. What if we do not control such a map or control such a margin? And what is the possible negative effect if there's no such a margin here?
If there's no
wait. Let the other audience try to answer. Do you prepare similar questions, or this is just questions coming out to my mind?
This is your question.
Okay, so maybe Ruofan, can you help me, or any volunteer to answer this question? Okay, if there's no volunteer, Ruofan, will you please point out one for me?
Xiangling.
You mean what if?
What if there's no such a margin here?
Then I think the point here is to distinguish positive samples with negative samples. So if not M, then maybe the distance can be equal. The D positive equals to D negative, and there's no such an effect to distance.
So isn't that good that if they're very large, and the larger the better? If they're very, very different, and I hope the distance will be very, very far away. Right, Dr. Xiao, do you know what if there's no margin here?
You mean if the negative one will be much further than the positive one?
Yeah, suppose two images are very, very different, and we let without a margin, and we suppose their distance will be very, very different, right? And why do we want to avoid such a case?
Yeah, if so, then I think it will have some problem during training because yeah, I think this is a training issue, I think.
And what is the negative effect during the training? What do you think?
I think it's hard to make the loss to be. You
mean decrease the loss? It becomes harder to decrease the loss.
Yeah, because if it is very, I mean, further away, then the number is.
It will be lost, right? The loss will still be decreased. Ruofan, what do you think?
So if without a margin, then all the positive will collapse at the anchor. Then all the negative are distributed very far away. This is a very strong condition, but we don't necessarily need that. We just need the positive to be a little bit closer than to the negative.
But when the isn't that good that if a very different sample to be very far away, is very far away from the positive.
We actually don't need that strong condition.
And what is the side effect, or what is the potential side effect if we reach such a requirement? If we do this, we push the very negative samples very far away. And what is this negative effect?
But all the positive will be at the same position as anchor. Then it's kind of overfitting.
I just say my guess. I'm not sure whether I'm also not sure because I haven't tried it personally. But imaginally, once Yuchen is here, we try to have such an experiment. The observation is that if we do not have the margin, or the margin is not small enough, the training computing power will try to keep optimizing the negative samples. So consider here. So we know that when we have a loss function, and suppose we have, so here in this loss function, we have many components here, right? So we can either optimize these factors or this component, or we can optimize this factor. If we do not have such a margin, it is very likely that we will keep optimizing this negative sample, but not optimizing these positive samples. So that is the case. So in this means the model keep learning the different sample, but will ignoring these positive sample. So this can be a side effect caused if we do not have the margin. Have I explained myself?
But I don't agree. I still think that the positive will collapse at anchor. I remember this point.
Have you tried yourself?
I didn't try myself.
Okay. So since I'm not going to have a strong claim, but based on, if I remember correctly, if there's no margins here, the model will likely to keep optimizing this negative effect, and it will ignore this positive effect.
Also,
because you can consider this positive. There's a bond for the upper bound, so we can optimize it to the 0, and that is so that.
Also that's what I mean. They collapse.
Let me re-explain. So suppose this component, right? This component range from 0 to positive finite, right?
Yeah.
And this sample is from the negative from negative finite but infinity to 0, right? Am I correct?
The same range.
I mean this one.
Okay.
So that means if we decrease the positive, maybe from the very initial stage, the loss for this component is 10, and then when we decrease to 0, it becomes much harder to decrease 0 to 1. Am I correct? Because the marginal benefits decrease.
Yeah, but also we don't need it to be 0.
Yeah, we definitely don't need to be 0.
So,
but in contrary, for the second component, if there's almost no limit when we try to decrease it. Right? We can always decrease into a more smaller or a smaller function here.
Yeah.
So if there's not a margin here, if there's no such a margin to add a penalty here, it is possible that the model will keep optimizing the second component and ignore these ignore to learn the distance between the positive samples.
Oh, I think it's not ignore because it already reaches 0, so it's not
No,
ignore.
no, no.
It's
I'm not saying
accurate.
I'm not saying it's reached 0. I'm saying that when to reach a certain point, it will not further optimize this component, because from the model point of view, it is more lucrative or profitable to optimizing the second option or second component.
I think they have the same gradient because they are all they're both in quadratic.
No, I
term.
don't think they have the same gradient because
They have
the
form of gradient.
but the
okay.
gradient is different. You can think about it. So suppose we increase the 2 and the 0 and the 2, and when we do the gradient descendant, this value will pass with the level 2, right? That means we change the weight. It will not change too much from 2 to 1. But if we change the weight, it can be changed from maybe -10 to -20. It is easier for them to do this, right? So in this case, the negative part will have more influence for the gradients.
Oh, okay. I think I get it.
Okay, so is that seems convincing? Okay, so this is just a discussion. I just throw these questions for discussions. Maybe we still need to further verification here, but that is my judgment when we learn the Siemens model 2 years ago. So this Siemens model is not trained well, and when we adjust the margin, and we do see the effect, especially we adjusted the margin so that we will not waste too many computing power to learn the negative sample, the distance of negative sample.
I think another reason may still be we don't want distance of positive to be 0. We don't require it.
Okay, so I think we can leave this question to be open, and the interested audience and students can think about this issue, and let's keep going on.
So the disadvantages of using this kind of training is because the training requires triplet, but if we look at our data, if we have n data points, then the total number of triplets is of order of magnitude. So here I want to ask a question to the audience. What do you think would be the order of magnitude for total number of triplets? Maybe Yufen?
B and triplet.
Yeah, so it's B because it's n truth tree, so it's of n to the power tree order. Because the number of triplets is actually exploding, so usually we do not train on all the triplets. We need to subsample some, then train on it. So we need to design some careful sampling strategy. One way to design such a sampling strategy is to sample those hard triplet. Hard triplet means.
Sorry, Ruofan. So, what is the citation of this paper?
Citation
of this paper, do you remember?
I don't remember.
Okay, so but it is actually proposed 2 or 3 years ago, right? This paper.
2020.
Oh, 2020, last year. Okay.
Yeah.
It's still not that old, right?
Top 3 performance.
Top 3. Okay, let's keep going.
So for example, we choose the triplet where D positive is large or D negative is small because it has larger room for improvement, etc. Another concern is because the contrastive learning only focus on one triplet at a time or only several triplets at a time. So it does not model the global relationship. Thus, it's not robust to our layers.
So this is very straightforward. Please raise any questions if you have, and if you're not clear the part. I think this is the fundamental problems of triplet loss, and this paper is supposed to address this triplet loss problem, right?
Yeah.
Okay.
So since triplet loss has some disadvantages, on the other hand, when we are using cross-entropy based loss, in the classification task, we can always achieve very good performance. The problem is that can we use some classification-like loss in metric learning task?
You're asking the questions?
It is the research problem of this paper.
Okay.
So in this paper, it proves the link exists between metric learning task and classification task. And then they propose a classification-based loss adapted for metric learning problem, which can surpass state-of-the-art.
It just published in ICSE, right?
Yeah.
According to, so Prof. Dong, in our group meeting, the Prof. Dong mentioned there's a core ranking. So, and I discussed with Prof. Dong and in the SOC committees. So we usually have an SOC ranking. And sorry for interrupting, just it just come to my mind, SOC ranking. But and this SOC ranking is very obsolete. For example, ICSE will be considered as second tier. So now we are looking to another two ranking. The first is called a CS ranking. CS ranking. So I think a lot of students know about CS ranking. So this ranking is used to rank a lot of research university. And another ranking is called a core ranking. So this core ranking is defined by Australia. So in the future, if we want to publish, it's better for us to just look into these two ranking, and then maybe core ranking will be the ranking used in our department in computer science department in the future. Okay, so maybe ECC. I'm not sure whether ECCV is ECC's ranking is in the core ranking, but in CS ranking, ECCV is supposed to be the second tier, right?
Yeah.
Okay. Let's keep going on. I just mentioned this ranking stuff briefly.
So this is the overview of my presentation. First, I will show that training a classification model is equivalent of maximizing the mutual information between class label and the learned embedding. And secondly, I will show that training a metric learning model is also trying to maximize the same thing. So then we can draw a link between two tasks. And then the paper proposed to optimize metric learning tasks in a classification way. So I will introduce some preliminary notations here. We have a data set D, and inside D we have input label pair. So YI are class labels. Then we have an encoder model phi W, which maps input to an embedding Z. If the task is classification, then we will have a soft classifier head following the encoder model, which further maps the embedding to a probability vector of K classes.
Okay.
So the embedding Z hat given X is just the output from encoder model when feeding X. And the classification prediction Y hat given Z hat is the output from classifier hat when feeding into Z hat.
Okay, I have no questions here.
So the first proof is we will show that training a classification model is maximizing the mutual information between class label Y and learned embedding Z hat. We will first look at the mutual information part. The definition of mutual information is given two random variables, X and Y. mutual information I, X, Y is equal to entropy of Px minus the entropy of Px given Y. It also has a second way of decomposition, which just swap the position of Y and X.
So this is just a mathematical transformation here, right?
Yeah.
Let me think. So is there any proof for such a mathematical transformation?
Yeah, I think so. I think if you expand, then these two are equivalent.
Okay, so
this is just saying, if you look at this term, entropy of Px given Y, then this is just saying, does knowing Y reduce the uncertainty in X?
okay, you are asking a question, right?
No, I'm interpreting the second term. So if knowing Y reduce the uncertainty in X, then this entropy of Px given Y would be small. Then this mutual information would be large. So here I have another question is, what is the mutual information when X and Y are independent?
Okay, you are asking a question, right?
Yeah.
Okay, so any audience or volunteer would like to have a try? Or anyone will try to have a guess here? Or Ruofan can try
Darren guess it is 0. Yeah, it's correct. So it's
okay.
0. Because when X and Y are independent, Px given Y is just Px. Because knowing Y does not help us to infer X. So this mutual information would be 0.
Okay.
So then we plug in the Y and Z hat because we want to compute their mutual information. And it's like this. If we only focus on the first way of decomposition, it's here. It's just the entropy of our class label minus the entropy of class label given learned embedding. Entropy of class label is the spread of class label in our data set. So it's the data set property. It is irrelevant to the model we learned.
Yeah, so, but my question is how to compute, but anyway, when we can calculate the entropy, we need to counting, right? Basically, we try to count it.
We take, this is the format, just the integral. If it's a discrete distribution, then you are doing counting. But it's a continuous one, then you do integral.
But here, the Py giving Z, we get this value by counting do the counting, right?
Do some density estimation.
So density is based on.
So counting is one of the methods in density estimation.
Okay.
Because you can have kernel density estimation, or you can have a simple histogram. Histogram is just your counting.
Okay. And so mathematically, they were using a density estimation so that it will be convenient for gradient descendant. Okay. So this is a very interesting observation. Okay, so I think that's more like a science. So this is a very good taste of the research, I think. So we do have intuition and how to vectorize or measure our intuition into a computable formula. So that is really a very interesting and important part for we to construct new methodology.
So actually here, we can interpret like this. If we want to maximize the mutual information, then we are actually reducing the entropy of y given learned embedding means that once we know the embedding from our encoder network, then we can infer y. So that seems to be aligned with the goal of training a classification model, right? Yeah.
Okay.
So a formal proof is that next we look at the left-hand side part, which is what is the objective for classification model. When we are training, we usually use the cross entropy loss. So if we expand the cross entropy formula, then it looks like this. The cross entropy between y and y hat. So,
okay.
So now we write out the left-hand side part and also the mutual information part. We only left with proof of the equivalence between the two. So through some derivation, do I need to?
You can try. I can try to follow.
So this is just formula. This is the formula.
So can you explain a bit about the y and the y hat and the z hat? Z hat is learning embedding.
Embedding.
Okay, so y hat is a predicted value, right?
Yeah. If you ignore z hat, then this looks like the cross entropy, right? This is just the cross entropy. It's just now we add z hat into it.
Okay.
Okay, and the mutual information, as I just said, I let the entropy of y to be constant because it's regardless of the model. And then I only left with the minus entropy part. So I expand it out. Now I want to prove that these two things equal.
Equal or similar? Similar, have some relationship. So I let this term plus this term, and becomes this. A plus or minus?
Plus, because here you have a minus sign, so it's plus.
And then this so this is the entropy here, right? Or this is entropy part, and this is
a cross entropy part.
Cross entropy part. Let me think about it. So why the cross entropy part will have the hat? And the cross entropy part, and when we calculate the cross entropy, we do not consider the learning embedding, right?
Yeah, but here is condition on the learned embedding. Maybe it's only considering training the classification hat.
Okay, so whatever, we can keep this hat here, whatever. So by right, if we want to show their difference, or if we want to prove they're similar, we should use LCE minus I, right?
Yeah.
And it's supposed to be a plus, if I understand it correctly.
Yeah, but later I will show that it doesn't matter. It doesn't matter.
It doesn't matter.
Yeah.
If we want to know A is element similar to B, we suppose use A minus B, not A plus B, right? And I think this does matter to me. Yeah. It does matter to me.
Because later I will show that this is a lower bound for this one. So you want to move this to the other side of equation.
Okay, so basically you mean that there have a difference of the
I think the term
KR divergence
is not very precise. Maybe I will show that they have some relationship, but not necessarily equivalence. Is
so basically it's just an estimation. So one formula will be an estimation of the other. Okay.
Yeah. So this is actually the KR divergence between y and y hat.
Okay.
So we have we have derived this equation, then we know that this blue part is the lower bound of the cross entropy loss part, since the KL divergence is always non-negative. So if we consider training a classification model as trying to minimize the cross entropy loss, then we can do this by minimizing the lower bound for it.
Oh, by the way, have you tried personally to deduce the formula? So anyway, in your presentation, you're capable to skip this formula induction.
I tried.
You try yourself on the paper, right? Okay, that's good. Then please go on.
So minimizing is equivalent as maximizing the minus of it. And because this minus is inside the mutual information, so it's equivalent of maximizing the mutual information. So we have shown that this claim is true. Yeah.
Okay, keep going on.
So we can also see from the equation, if you want to minimize the CE loss, it can be minimized by either minimizing the first lower bound or the second term KL divergence. So we can have an interpretation of the classification training as a minimize game. We iterate doing the following two steps. The first step is we fix the encoder weights, then optimize the classifier hex weight. That means we fix the this part and then minimize the KL divergence part to have zero divergence. And step two is we fix the classifier hex weights and then optimize the encoder. That means we fix the second term and minimize the first term. So these two lower bound are minimized in turn, such that the sum is minimized.
Let me think about it. So minimize the HZ, and can you remind me of the formula of this one? So my basic question that why we cannot train them all together, and we need to train
it's an interpretation. When we are doing training, we are training together, but here is an interpretation.
Okay.
So it's something like you are training the autoencoder, although you train the encoder and decoder together, but you can view it as you fix encoder and train decoder, and then you fix decoder and train encoder. You can view it as such a game.
Okay.
So secondly, training a metric learning model is also trying to maximize the mutual information. Recall that for the mutual information definition, we have two ways of decomposition. So previously we focused on the first way, and now we focus on the second way of decomposition, which is the entropy of Z hat minus the entropy of Z hat given Y. So if you want to maximize the mutual information, I should maximize the entropy of Z hat. Means that by embedding Z hat should spread all over the spaces. And if I want to maximize mutual information, I can also minimize the entropy of Z hat given Y. That means given a particular class Y, I want my Z hat to be clustered. So that is the same as the goal in metric learning. Because we are pushing different classes objects far away, so we are increasing the entropy of Z hat. Also, we are pulling the same class objects to be close. We are decreasing the entropy of Z hat given Y.
Okay, interesting.
So I wrote out some proof in my slides, but for now I will skip it.
Okay.
This will formally show why the positive distance part is proportional to this, and the negative distance part is proportional to this.
But this form is still kind of the triplet loss.
Yeah. So because the claim here is to show that is, yeah.
Okay, so in a question here, I think Ruofan gave a very good presentation and especially in the theoretical and mathematical interpretation of the triplet laws. So any question to raise here? If no questions, let's proceed.
Now we have proved claim 1 and claim 2. So we know that although metric learning seems to be different from classification task, but the goal they are maximizing is the same. And metric learning is constrained by the sampling strategy we use, while classification model does not require designing sophisticated sampling strategy or weighting strategy, etc. So can we use some classification-based laws in metric learning to improve its optimization process? So the other design cross-entropy loss for metric learning. It tries to minimize the embedding distance of the same class points as maximizing the probability of assigning to that class. The probability of assignment is the affinity to that class centroid. So this is a loss. It looks like a cross entropy, right? And the numerator is, well, we're trying to put Zi. Zi is the embedding for current data point, Xi, to be close to the central embedding of class Yi. Yi is the class label of Xi. And the denominator is Zi's distance to all class centroids. So this is like what I mentioned, the probability of assigning to that class.
And how many centroids are there?
If you have K class, then you have K centroids.
But it is also possible that we can have multiple centroids for a certain class, right?
Yeah.
You will cover this later.
This is not in this paper, because in this paper they assume there's only one class, one centroid.
Okay, then I think the active learning is kind of straightforward if we just measure the distance for the new sample with existing centroids, right?
Yeah, so I feel if I want to do active learning based on that loss, then it's actually active learning for classification.
Let me think about it. And also we can consider it as an entropy. So is it possible that we think about it from an entropy point of view? So that means when we have a new samples, we evaluate this distance with the different centroid. Maybe let's have a try, because it seems to me that it's low hanging fruit, which no one have working on this. Maybe simple approach with simple proof. Maybe that's just enough.
I try to compute like the top one.
And also you can think about it, because one of the major difference between the classification and this metric learning is that the metric learning is supposed to adapt to unseen class, right? So you can think about it, whether it make a difference if we select a sample from non-class or a sample from an unseen class, right? Whether there are any difference there. And it is supposed to have larger distance or smaller distance, or and what is supposed to be, and we can also have an estimated inference. So I'm not sure whether the model, introducing a new auxiliary model is good enough, but anyway, we can estimate the inference or the Shapley value when we add a new samples into the original model and make a prediction of its Shapley value or inference. That might be a way to go. Okay, let's keep going.
So it turns out that designing the metric learning in this way can have easier optimization process. So this is the original sentence from the paper. They say that cross entropy contains only unary terms, while the traditional deep metric learning are based on pairwise term optimization. So this requires sampling the pairs, or the triplets.
Mm.
Yeah, in my opinion, I think the softmax loss can produce stronger signal in optimization, because I think adding log or exponential can aggrandize its gradient.
And in my interpretation, I just say that's my interpretation, not 100% correct. I think it actually, because this is just decided by the batch size, right? Suppose we have a large batch size, we're comparing one angles with multiple positive and negative samples, right? And when we have angles, we just to compare them pair by pair. But if we're using classifications, we compare them. I don't know. Maybe we compare them all together and have a stronger contrast when force the model to learning, right? So basically, we can see that the model structure is just there. So the number of weights is just there. All what we've done is just change the loss function.
Yeah. Right.
So, and even for batch size, I think we are, or maybe the batch sample is different, right? But we allow the classification model, the loss of classification model allows more sample to interact with each other, or they have a more specific direction to learn. And if we have triplet loss, and then maybe the direction is not that sudden, sometimes we go left and sometimes go right. But just like we are doing a research task, right? Suppose we have a very clear task, definitely we will be more productive, efficient. But sometimes the goal or the task is a little bit vague. We sometimes think right and sometimes think left. Sometimes we do this and sometimes we do that. And our learning or our efficiency will be largely influenced, right? So maybe that's just that not that appropriate metaphor, but basically convey the basic idea. When we design a loss, we need the model to learn with a strong with strong direction instead of a weak, not a direction with less strength.
Yeah.
Okay, let's keep going.
I agree. I think using this kind of loss is optimizing in a more holistic way. The experiments is based on 4 data sets, which are commonly used in metric learning tasks. First one is it contains birds of 200 species, and the second is it has cars of 196 brands. And we also have online products data set and clothes retrieval data set. The evaluation metric we look at is called recall at K. That means for every data in the evaluation set, we find its K nearest neighbor within evaluation set. If any of the neighbor has the same class label as query data, then we count as 1.
Okay. So anyway, the results showing that they did a good job, right, in many architecture.
They use ResNet.
And there's a Google Net.
Google is for baseline.
Okay.
Last row is this paper. The above rows are baselines.
Okay, let's keep going on. So so it's come to the end of the talk, right?
Yeah.
Okay.
So we have verified 2 interesting claims, and then we find that cross entropy loss does it all. It can be adapted to metric learning and have better performance.
Okay, thanks Ruofan for the very clear presentations, and I think that the major. So think about it. So this topic from the technical level, it changed the loss, right? It introduced the idea of a proxy or centroid and change the loss, and that's all. But it have I think it have several pages to discuss the insights why it introduced such a loss, right? So I think we do not need to worry about the techniques. It's too simple. Let's make the effect come out let's make the approach effective and outperform all existing baseline. And then we have enough leeway to think about the theory and so on. And I think we have this topic because our observation when we're working on a single tail project, when we're using triplet loss, the effect is very poor, right? We think about a lot. We try a lot to train assignments. We put a lot of time, spend a lot of energy to train the triplet loss, but it does not work. But anyway, after we're using the classification model, it just work. But just for application level. Now we have and this paper from a theoretical point of view, align with our observation and application, and we can think more through this direction. And the result, and that also comes a lot of research opportunity. Okay. Thanks again.
Can I ask a question? So so the main, conclusion is that if we can change the loss function, then I still confused. So it changes the triplet loss function into another new function.
Yeah, it will be more effective to distinguish the embedding.
So that to make the same label, the embedding
further far away.
The same label is closer, and the different label has for the Then which kind okay.
Maybe Ruofan, you can share the slides again to show the loss function. Yeah, maybe Dr. Xiao, you can check the paper, and the paper is just in our. So here we can just change this loss, and according to this paper, ICSE 20, this loss will be more effective than a triplet loss.
So because I remember there is a figure in your slides shows that it's 11. So that means previously we will use the z hat, then to learn the triplet loss.
Yeah.
Then now we
still use z hat.
Yeah.
Yeah.
But change it to be similar to classification.
Yeah. So the idea is that if the loss is designed more towards classification sense of point of view, it might be more effective. And here there's the proof here, right?
So the distance to class centroid can be viewed as probability of belonging to that class.
Do you mean that they put all the positive samples to be close and just put the positive samples?
And I think it's choosing a representative of the positive samples and classify and optimize the model towards that representative. Okay, I think it is a very interesting topic, and I encourage we have offline discussions in the group, and that will be very great. Okay, is there any questions there? If there are no questions, let's thank Yuchen and Ruofan, and I think they prepared a very good presentations, and let's meet in next week. Okay.
Okay. Hi, Dong-Ling. Can we have a short chat after this? Very short.
Okay, sure. Okay.